welcome to the Week 8 review for Math 2413. In this review, we'll be going over just a couple of practice problems with derivatives, but mostly we'll be covering related rates and differentials. So let's go ahead and get started. We're just going to start out a couple of review problems for derivatives because you're basically going to be using derivatives for the rest of the course, so I want to throw a few more practice problems at you. So your job is to just find the derivative. And neither of these are too terribly difficult. But they do cover a couple of the things we talked about last review session. So I'll give you guys a couple of minutes to work on those, and then we'll go over the answers and then jump into some related rates. Good luck. Alrighty, we've got an answer for part A. Let's go ahead and run over that really quickly. So, and an answer for part B. Perfect. So let's run over these problems. So for our first problem, what we have is we have to take the derivative of log base 10. Now, the derivative of log base 10 is going to be 1 divided by the natural log of 10, so the natural log of our base, in this case is 10, multiplied by the inside, and then we multiply all of this by the derivative of the inside. So the derivative of 2x squared is 4x, and then we can simplify. We can cancel an x and a 2, so that gives us 1 over x times natural log of 10, and we should still have a 2 on top. So our first derivative is 2 divided by x times the natural log of 10. Perfect. For our second one, we again have to use our rules for taking the derivative of an exponent that is not e. So that rule is we take the original thing, 2 to the sine of x, multiply by the natural log of the base, so the natural log of 2, and also multiply by the derivative of our exponent. So the derivative of sine x is cosine of x. And this would be our answer. We can't really simplify that at all. Not too bad. All right. So we'll probably start off a lot of these other reviews with just a couple of quick practice and problems for derivatives, just so you guys don't forget all of your derivative rules. But that was a couple of practice problems. Now let's get into something that's really fun, related rates. So the whole idea behind related rates is that if two things are related, well, then their derivative should be related as well. So let's just go ahead and start out with an example problem. Just a really simple example. Let's say that we have a volume of a sphere. Well, the volume of a sphere is 4/3 times pi r squared. So here we have a relationship between volume, sorry, that should be pi r cubed. And here we have a relationship between volume and radius. So the principle behind related rates is because volume and radius are related, well then the derivative of volume should somehow be related to the derivative of the radius. So if we take the derivative with respect to something like time, well then we would get, using our power rule, that our derivative of volume is related somehow to our derivative of the radius, the rate of change of the radius. So what's a situation where this might be occurring? Well, let's say you're filling up a balloon. The classic example is filling up a balloon. And you wanted to find out how fast the radius was changing if you're putting in 10 centimeters cubed of air every second. And the current radius is, I don't know, 10 centimeters. So if you had a balloon that had a current radius of 10 centimeters and you were putting in 10 centimeters cubed of air per second, well then you could find out how fast the radius was changing. Simply because this is the change in volume, this is the current radius, so then we can say that 10 centimeters cubed per second is equal to 4 pi times 10 centimeters squared times dr dt. And then that would imply that we could find our rate of change of our radius. And that would be 1 over 45 centimeters per second. So let's do a slightly more complex example. Let's say we have a water tank, and it is in the shape of a cone. You will see all kinds of problems using water tanks, using balloons, using piles of sand, things like that. It's just going to be the same problem phrased differently. So let's say we have our water tank. I'm going to draw a nice picture. I can make it big. So there's our water tank roughly. And it is 20 meters tall. It's a big water tank. Very big. And right now, though, it's not entirely full. It has some water in it, but only up to about right here. And this line occurs at 12 meters. And we also know that the radius of our water tank is exactly 4 meters. So my question is, if I'm putting in water at a rate of 5 meters cubed per second, well then, how fast is the height changing? How fast is the height of water in the tank changing? Well, there's really a whole process to solving related rates. Give me one moment, we're having some issues with the projector in here. All right. Back to this problem. I'll do a free one on whiteboard in a sec.
Should I just join?
If you want. So back to this problem. We're looking for how fast the height is changing. And I was saying that for related rates, there's a whole process to each of these problems. What you want to start out by doing is by essentially writing an equation relating your quantities. So in this case, I'm looking to write an equation that relates volume, because I'm given dV over dt, and probably height, because I'm looking for something related to height. Well, I know the general formula for the volume of a cone. The volume of a cone is equal to 1/3 times pi r squared times h. So the problem with this equation, though, is that it has two variables in it. It has radius, and it also has height. But I don't particularly care about the radius. I'm given the radius, sure, but I'm only interested in how fast the height is changing. So there should be some way for me to reduce this problem so that it's only relating volume and height. Well, if I draw a cone from the side as a two-dimensional triangle, what I have is it's 20 meters tall and 4 meters wide. So I can actually relate my height and my radius, because at any given height in here, I know that my triangles should be proportional, which means that if my current height is 4, or sorry, if my current radius is 4 and my current height is 20, that should be equivalent to any current radius over any current height of any similar triangle. And what this does is it gives me an equation. If I cross multiply, I get that 4h is equal to 20r. Or in other words, r is equal to h over 5. And that gives me an equation that I can use to substitute r out. So then my volume is 1/3 times pi times h divided by 5 squared times h. And that is 1 over 75 times pi times h cubed. Make sense? All right. So now that we have a formula for volume in terms of height, well, I can say because my volume is related to my height, the derivative of volume should be related to the derivative of height. So I just take the derivative of each side, and I get 1 over 25 pi times h squared times dh over dt. Well, I'm given my h value. I'm given that h is equal to 12. I'm given dv over dt. And that's really all I need in order to solve. I can simply plug in 5 meters cubed per second, equal to 1 over 25 times pi times 12 meters squared times dh over dt. So then I get that 125 divided by pi is equal to 144 dh over dt. I kind of dropped my units. I should probably include those. Let's see. I'll rewrite it with units. So on this side, we still have meters cubed per second. And on this side, we have 144 meters squared times dh over dt. Now, I just divide by 144 meters squared on each side, and I get that 125 over 144 pi. I divide both sides by meters squared, so I'm left with meters per second. And that is my dH over dt. Not a pretty number, but we solved for it, so any questions? Why did I plug in 12 for the height and not 20? So the thing is, that's a good question. The answer is because the height of the water currently is 12 meters. One thing you could think about is, what if I just made the height of my cone, well, 12 meters taller? What if I just made it keep going? Well, then it could be really however tall I wanted, but the rate of change of the height at this point should stay the same. So the reason is I'm only looking at the current height of the water. Because if I was looking at the total height of the tank, then, well, the tank could be really just as big as I wanted, but it shouldn't change how fast the water is rising because this bottom portion is the same regardless. The reason this 20 was important is because we only knew the radius at the top. So that 20 and that 4 allowed us to set up this relationship between the radius and the height, which then allowed us to substitute out our radius in our volume equation. Does that make sense then? Instead of replacing the radius with its relation to h, you know that dr dt is 0, so it cancels itself out. Let's see. I mean, we could possibly. Let me see if I can work this out your way. So you're saying that we don't need to replace our radius, right? Well then, in this case, I would say that dr over dh is not actually 0. So let's see. If we did just take the derivative without substituting out h, or without substituting out r, well, then we would have to use the product rule between r and h. So this would give us 2r times h times dr dt plus r squared times dh dt. That's just the product rule between r squared and h. We're looking for dh over dt. The thing is, we still have this relation that r is equal to h over 5. So at some point, we would need to substitute out dr over dt, because clearly if we take the derivative of this equation, we get that dr over dt is 1 over 5 times dh over dt. So if dr over dt were 0, then dh over dt would also have to be 0, and that's just not right. Yeah. If we had a cylinder, then we would have dr over dt, so thank you for pointing that out. Yes. That is another way you can do it. It's just basically changing when you're making a substitution. So you could either make your substitution before taking your derivative, which is what I did in the original example. Out here, though, here I took my derivative first, and then we would have to make this substitution right here to get rid of dr over dt. But good question, good question. All right, are we clear on this example? All right. Then let's move on to some practice problems. We'll start out with an easier one, and then I'll give you some more fun ones. So here we go. And these are going to be some very fun stories. So let's say we have a stone and it falls in a pond. And a ripple goes out at 2 meters per second. And I want to know how fast is the area of the circle inside the ripple, changing if the ripple has a radius of 4 meters. All right, does everyone have like a picture of what that is? It's not like a confusing, weirdly worded problem or anything. Practice problem. Perfect.
To be fair, even if I hadn't had all the time because it went out, I still don't know what I'm doing. So I wrote 2 meters. Is the radius, is the area of the circle 4 pi r squared?
It is just pi r squared. They're thinking about surface area of the sphere. That's equal to pi r squared.
So I'm thinking if it comes out at 2 meters per second, that's the area.
Well, the ripple is moving on at 2 meters per second. What do you do next? measure a box with just a meter stick? Right, we would need meters in two directions. So our for units for area should be meters squared. So there we're just giving meters per second. So is that area that you're given? So what rate? Right. Speed is changing something, right?
Change of distance over time.
We are changing our radius over time, right? And then because it's per second, that tells us speed times per second. So that's kind of one key thing in these sort of problems.
So speed is the derivative, or how fast the derivative is moving?
Speed is the derivative. So speed is the rate of change of something with respect. You're saying 5 over 12 pi for number 2. And to that I would say, you got 5 over 4 pi, okay. Neither of those are actually what I got for number 2. So it's possible that I'm wrong. You both have similar answers, but not quite. So we will see in a second. Did you get a chance to finish up number 1?
No, but we can move on. I don't know.
Derivative is what? Change in area with respect to time, right? Well, you wrote your equation. I squared, right? Well, how can I get
Divided by 10.
well, I can take the derivative, right? We don't divide by time. This isn't really division. But we can take the derivative to get to A, right? So if I take the derivative of the left hand side, what do I have to do the other side?
Take the derivative
Okay. So the derivative is
of pi r2.
2.
2 pi r.
Right, but then when I take the derivative of r, I also need to multiply by.
The derivative.
I need to make sure this is sneakily interchangeable. But you need to make sure you're including that part. Do you have enough information to solve for dA over dt now?
Yeah.
All right. Let's go over these questions. So for the first one, we always, or at least I always like to draw a picture. So here's our picture. I'm going to use blue because water is blue. Here we have a ripple, and there's our radius, or our radius is 4 meters currently, and it is expanding outwards at 2 meters per second. And specifically, we are asked to find dA over dt. And we know that dr over dt is 2 meters per second, and r is equal to 4. Well, the area of a circle is pi times the radius squared, so then we can get the derivative of area by taking the derivative of each side. Derivative of pi r squared is 2 pi times r times dr over dt, and then we can just plug things in. And that is, of course, 16 pi, and that should be meters squared per second. I kind of left off my units, but for the 4, we have 4 meters, and for the second, we have meters per second, or dr over dt. So yep, 16 pi meters squared per second. Good, good. All right. Everyone clear on question 1? All right, let's go over question 2 then. Okay, so first off, we should write down what we're given. We know that sand is falling on a pile at a rate of 10 meters cubed per second. So that tells us that our change in volume is 10 meters cubed per second. We also know that the height is equal to half the radius. And we're given that our current height is 6. And lastly, we're asked to find the rate of change of height. So because this is a pile, we can kind of know that this should be a shape of a cone, because that's the shape that sand falling on a pile makes. I probably should have stated that more explicitly, but we have a cone. We know the volume of a cone is 1/3 times pi times the radius squared times the height. In this case, we're lucky enough to actually have a relationship between radius and height already. So if I wanted to get radius by itself, I could multiply both sides by 2. So radius is twice the height. Well, then I can substitute this in and say that volume is then 1/3 times pi times 2h squared times h. So volume is 4/3 times pi times h squared cubed. Now I'm ready to take my derivative. I'm looking for dh over dt, so I'll need to take the derivative in order to get that h. Oh, you thought it was a cylinder. Okay. Right, yeah, that would get you a different answer. Yep, that one might be on me. I probably should have stated that more clearly in the problem. We'll just put this in there. There, now it's a cone. And you messed up on squaring 2h. I don't know if that would have gotten you as far off as you were, because 4 as a denominator doesn't seem quite right to me. We'll just finish out the problem. I'm going to move this up to the middle. E equals to 4/3 pi times h cubed. So if we take the derivative, that would give us 4 pi times h squared times our derivative of h. Perfect. Well, now we know dv over dt, and we also know h, so we can plug those in, and that gets us 10 meters cubed per second is equal to 4 pi times 6 meters squared times dh over dt. So then 10 meters cubed per second is equal to 4 pi times 36 meters squared times dh over dt. And now we can divide both sides by 4 pi times 36 meters squared. And I'm going to turn this into a 5 and this into a 2 before I start. So then I have 5 divided by 2 times 36 is 72. I still have my pi. Now I have meters cubed divided by meters squared leaves me with meters. And I still have my divided by seconds. So the answer is 5/72 pi meters per second. Does that make sense to everyone? All right, perfect. In that case, I'll go ahead and write down the next practice problem. Because I like related rates. So,
Can I see your work? Or does your paper have work on it?
it has some. I don't know if it'll work. Give me one moment, y'all.
It's so tiny. I was like, I'm sure it looks tiny because it's such a big screen. No, you're right. It's small. No, aggressively keep clicking it. And like, to like, oh shoot. Yeah. should really be on.
All right. Let's see. So for this next practice problem, we're going to have some trains.
Don't you need this? For the
Yes.
train problem?
So let's say that we have one train, and it goes north at 15 miles per hour. And we also have another train and it goes, let's say, east at 20 miles an hour. Well, I want to know, after 2 hours, how fast is the distance between the trains changing? And there are going to be a lot of variations on this problem that you will probably see. Sometimes you'll see cars, sometimes you'll see boats, sometimes they'll leave at different times or go in slightly different directions, stuff like that. So we'll start off with the basic one, and if we have time, maybe I'll do some more exciting ones.
No, I just realized that the only thing that I wrote down is that I didn't realize that this was like this and then we did stuff, so I I think I understood it. I don't think I can recreate it just yet, but with a bit more practice.
All right, sure, we'll do a problem with the rate that an angle changes. I actually had that one slated for a bit further. Maybe, I don't know, 5 or 10-ish minutes. Okay, problem didn't seem to be too difficult for you guys. If you thought this one was too easy, we can always change up the angles on this, but yes, they do start at the train. Yes, they do start at the same spot. Yeah, let's see. As it is, this problem isn't too hard. If you want a bit of added challenge, you can have them I'm going to label this train A and this train B so I can differentiate them. A starts, we'll say,
Can you scroll up?
or so those are a couple of variations that you might see where one train leaves earlier or one train is going not just in one direction, might be heading northwest rather than just north. Now, if anyone wanted to look at the previous problem, here it is as well, and I'll just give you a couple more minutes to work through this. And if you thought this one was too easy, there are a couple of challenge ones you can work on as well.
Okay, so the volume is that. So you started off at a, what's this?
That is the formula for, so that is the formula for 1/3 pi squared.
Okay, and then that is,
I were given it I use the radius divided by 2. So then I substitute out the radius because I don't know what it is.
oh,
And I also just want to get the simple, right?
and then that's just you multiplying it out. So the volume is that the substitutions. And then, so we're not finding the derivative of h, but we can find this first and then.
Well, we do want the derivative of h. What I know though is that because my volume equation has an h in it, if I take the derivative of my volume equation, I should get a h. So that's why I keep the derivative, because I want to get to this h. Does that make sense?
So that's, and then times that, but we don't know that.
Right. That's what we're doing.
So then, what did you do to find it?
Well, do we know the yield? No. No, it's given in the problem, right?
Oh, I thought, oh, I wrote the
Oops.
So the rate is the rate of what? That's changing.
Sand that falls on the ground. Remember the big hint? Units. That's meters cubed, right? Well, meters cubed is volume. Right? Because if you were to measure the volume of the box, you need to measure it in 3 different directions.
So then, okay, so then 10 is 4 squared times 4. And then we just solved it.
Also knew h, right? That was also given in the problem. And then we know everything in there except for h to t, right? So we can just solve it.
And then that equals 5.725.
Now then, in order to get around to the rate of change of an angle problem, I am going to kind of rush through this example here. Is the northwest problem doable without any angles? Yes, actually. So we'll take a look at a setup for that. I probably won't actually work through the whole thing, but I will show you the setup. And well, it's doable without like using the derivatives of any angles, I should say. You would probably need to use a little bit of trig. I just need to wait for OneNote to finish lagging. There we go. Perfect. Okay. So miles an hour. So then the distance between them would just be the side of this right triangle. And I should use something other than d. I'm going to use L for length, I guess. Well, after 2 hours, we know that train A should have traveled 30 miles because we have 2 times 15 miles per hour gives us 30 miles. And we also know that train B should have traveled 2 times 20 miles per hour or 40 miles. And we also know that a relation between these two things, or a relationship between where train A is and where train B is and the distance between them, can be found using our Pythagorean theorem. So then if I take the derivative of this Pythagorean theorem equation, I should get 2 times the distance between them times the rate of change of the distance between them is equal to 2 times A times dA over dt plus 2 times B times dB over dt. Well, I know dA over dt, that's just 15. I know dB over dt, that's 20. I also know A and B. This is 30 and this is 40. I can also figure out L because I know that L squared is equal to A squared plus B squared. In this case, L happens to be 50 miles. One way you can actually do this without using a calculator or anything is this is actually 10 times a 3, 4, 5 right triangle. So a 3, 4, 5 right triangle is one of your special right triangles. So we know that this triangle scaled at all should have the same proportion. So in this case, we have a triangle of side lengths 30 and 40. The third one should be 50. Well, now we know everything we need. We can plug things in. 2 times 50 times dl over dt is equal to 2 times 30 times 15 plus 2 times 40 times 20. So then dl over dt, I believe, should come out to 25 miles per hour. All right. So now let's take a quick look at how you might want to set up the problem where train A is heading northwest instead of north. So again, we're actually going to want to draw out a picture. We have train B, it's going this way at 20 miles an hour. Now we have train A going, if I can draw a straight line, northwest, which is this way, at 15 miles an hour. Well, I can actually break down the speed of train A into components. So if I drew this out, I'm going to have one component in this direction and one component in this direction. And because I know this angle here is 45 degrees, because that's exactly the direction of northwest, I would be able to figure out the length of this vector component here. In this case, it would be 15 times the cosine of 45, which is 15 root 2 over 2. And that would be our rate of change of A in this x direction. So then if we wrote this out in one combined triangle, we would have something like this, or in reality, this is our origin. This is our vector A. This is our vector B. So this is the train A, this is train B. But then all of this is the combined A and B, and this is the combined A and B as well. So we could actually write this out as this side length would be the horizontal component of A, so 15 root 2 over 2, plus the speed of B, so plus 20. And this vertical component would be 15 times the sine of 45 degrees, which is also 15 root 2 over 2. So again, we could write something to find the length between the trains. Did I use special right triangles? For the original problem, not for this variation. For this one, I just constructed my right triangle right here, and then I used trig to determine the components. So I broke up my train A into a horizontal component and a vertical component so that I could put that into a right triangle. For this first part, though, yes, I did use special right triangles, because I just like special right triangles. Okay, yeah, so the root 2 just comes from using trig to find this component here. because I know by definition of the direction northwest that we're just going in a direction that's 45 degrees to the north of just straight west. So that gives us a right triangle that we can then use trig on, like right there, to break our vector into components. All right. I'm not actually going to go through the solution of this one though, because I want to actually hit that problem about the rate of change of an angle. So we're going to move on to that one now. Okay. So let's say that a person is standing on the ground and they are watching a balloon that a child accidentally let go of. So this balloon is floating away. It's currently at a height of h, and the man is standing 20 meters away from where the balloon is. So if the height is changing, if the balloon is rising at 3 meters per second, I want to know how fast is the angle of elevation changing? Or in other words, what is d theta over dt after 5 seconds? And I will give you guys a couple of minutes to work on that.
I don't understand this. So I get how you found that. So that's 2 times a. Why do we still have to multiply another 2 if we already did it up here?
Well, if we take the derivative of this, right, because we're taking the derivative of L squared times A squared to give us 2L, right? What's the derivative of A squared? So that's what that's about. So we have 2A times dA over N, and that's what this is. Does that make sense?
So, okay, L squared. Well, we already multiplied it here. What if we hadn't multiplied it? Like, do we have to because of the 2 hours?
So we have the 2 hours, so that's where we get specific. The distance. So that's what A comes from. This 2 is wholly separate from 2 hours. This 2 comes from taking the derivative. The 2 times 15 comes from the 2 hours.
Okay, so we have this equation, and this equation is the derivative of this equation. So this would be 2L times 2A. So then the derivative of A is 15.
Right, it's the rate of change of
Because since it's changing, that's already a derivative.
right. So this is A, so it's we have 15, so that's how we have that.
I wouldn't be able to read this.
Would you like me to do another kind as well? It's not like I just made this one.
This one's harder than this one.
Usually people tend to struggle a bit more with the angle ones because it involves trig. So I can give you one similar to this, which you can flip this time if you like. Alright. So again, I'm really hoping this one is going to work. you had
Your head is very symmetrical.
Thank you.
Actually gonna be pretty easy.
Huh?
Let's copy on the better.
No.
I'm measuring color in a very weird way. So.
All right, and how is everyone online doing with the super fun balloon problem? Oh, I actually forgot to draw the balloon. There we go. Perfect. Good, except you got arctangent for your angle, so you think it's wrong. Okay. Well, that's fun and exciting. What did I get for my angle? Perfect. Is there a way you can use your triangle in order to solve for that angle? Right? Let's see. Is everyone ready to go over this problem? All right, cool. I'll just start going over it because I do want to touch on differentials at least a little bit. So, starting out with this problem, we need to find a way to relate our height, because we have dh over dt, with our angle, because we have d theta over dt. Now, the easiest way to do that would be through trig. Because we're given the opposite side and the adjacent side, I would use tangent. And tangent of theta is equal to opposite over adjacent. Now, if I multiply both sides by 20, because I'm not trying to use fractions here, I get that 20 tangent of theta is equal to h. So then when I take the derivative of this, I get that 20 secant squared of theta is equal to dh over dt. Oh, I forgot to include. So when I take the derivative of 20 of times when I take the derivative of 20 tangent theta, I have 20 times secant squared of theta times the derivative of theta, because that's what's on the inside. And that is equal to dh over dt. Okay. Perfect. So, well, now I know what dh over dt is. I'm looking for d theta over dt. I don't necessarily have theta here. So, we need to be able to find theta. After 5 seconds, because dh over dt is 3 meters per second, h would then be 3 times 5, which is 15 meters. So then I have a triangle that looks something like this, 15, 20, and I'm looking specifically for theta. So if I know that tangent of theta is equal to 15 over 20, well then theta is equal to the arctangent of 3 over 4. So yes, you do actually need trig. But then the thing is, I don't want to leave an answer in the form, if I plug in this theta and my dh over dt, I don't really want to leave arctangent, secant squared of arctangent of 3/4 in my answer, because that's kind of a not very pretty number. Oh, I know dh. No, I'm looking for dh over dt. Perfect. Equals to 3 meters per second. There we go. dh over dt. All right, so now the question is, how can we simplify all of this? Well, I know that arctangent tells us that we can construct a triangle with a given angle theta that has an opposite side of 3 and an adjacent side of 4. Well then, because this is a special right triangle, then I know the hypotenuse should be 5. And I know what secant of theta means. Secant is 1 over cosine. And cosine theta is, in turn, adjacent over hypotenuse. So then secant of theta should just be my hypotenuse over my adjacent side. Well, I know what my hypotenuse is. I know what my adjacent side is. So then the secant of theta in this case is equal to 5 over 4. So then the secant squared should be 5 over 4 squared times d theta over dt is equal to 3. Does everyone understand how I got there? Right, so basically what's going on here is whenever you have trig and it looks like this, where you have one trig function and the inside part is an inverse trig function, well, your inverse trig function is actually telling you, when I give you a triangle, specifically because this is arctangent, the way we can interpret arctangent of 3 over 4 is saying, well, when I start out with a triangle, specifically with an opposite side of 3 and an adjacent side of 4, because tangent is opposite over adjacent, well, arctangent will start with this triangle and give out this angle theta. So then when we take the secant of this angle, well, the secant works on the exact same triangle. So we take this angle theta for this same triangle, and secant says, well, I'm going to take in this angle theta and give out my hypotenuse divided by my adjacent side. So because our arctangent allowed us to construct this triangle, we can use our secant to pull the information back out. So take out 5 and 4, and that would give us the secant of theta being 5 over 4. So it's not that it's equal to secant, it's not that arctangent is equal to secant, it's that using the arctangent we could construct the triangle that we would then use to solve for what secant of theta is. Does that kind of make any sense? Yeah, so just to reiterate, our whole principle is our normal trig functions take in an angle and give out some kind of triangle looking thing. Well, our inverse trig functions take in a triangle. So I'm going to just put a triangle in there and give out an angle. Specifically, instead of a triangle, it's more of like a ratio between sides of a triangle. So arctangent takes in the ratio 3/4. But you can think of it as if I'm given an arctangent, the arctangent takes in a triangle, 3/4. So then when I take that triangle, I can find the angle and then use that triangle and that angle to find my secant of that angle. All right. So we're almost done with this problem. We've simplified it down to this. So this makes 20 times 25 divided by 16 if I square my 5/4. d theta over dt is equal to 3. So then I have d theta over dt is equal to, if I cancel, this is 4, this is 5. Well, then I have 12 over 125, and this would be radians per second. So that would be our final answer. Questions? Will they ever give you a related rates problem with acceleration? I haven't seen it before. That's not necessarily to say that they won't give you a problem with acceleration. They might start it out with like velocity and ask you, because acceleration is just the first derivative of velocity. I've never seen it done with acceleration though. That could be an interesting problem. All right. Let's talk briefly about differentials, because I believe you do cover them, or did cover them pretty recently in class. So the whole, and really we'll just start by trying to get a big picture of what a differential is. So let's say you have a function, and it looks something like this. Well, let's say you also know the value of your function at some point A. And you also are interested in finding out, well, what's the value of my function at this point X? Well, what if f of x is really hard to find? Like, it would just include like a lot of really intense calculations. Maybe it's like the square root of 4.01. Well, that's not very pleasant to work out. You'd rather just do the square root of 4 exactly, because this one's easy. Well, differentials are a way of approximating these function values. So if you know f of a, well, then you can kind of construct a tangent line to your graph at this point A. I should have made this a much steeper curve. But basically, you could have like a tangent line, something like this. It's not quite tangent because I'm not good at drawing. Here we go. We'll just do this. There we go. That's a steeper curve. So you have a tangent line right here. And again, it's only roughly tangent because I'm not good at drawing. And this is now point A, and this is point X. Perfect. I am all over the place right now. I'm sorry. There we go. All right, here's our picture. So basically, our differentials, the idea is if we have a known point at A, so we know the value of f of A, we're trying to approximate the value of f of x. Well, the distance between A and x, we're going to call delta A. And then we're going to call this little distance delta y. And the idea is that this third distance, the distance between our tangent line approximation and our actual value, very small. We're just going to say that it's very small. And basically the idea is the smaller this red line is, the closer our approximation is. So in general, we're going to make our approximation by saying the value that we want, f of x, is about equal to the value at our point A plus our change in y. But our change in y we can actually represent by saying, well, change in y is really just the derivative multiplied by our change in x. In other words, it's the slope of our tangent line multiplied by however far over we went. So that's kind of the big picture idea of differentials. You're going to say a point that is unknown is about equal to a known point. That should definitely be a plus right there. Plus the slope of your tangent line multiplied by, and really this should also be an A, sorry, multiplied by however far over you're stepping. So let's do a quick example. Let's say we wanted to approximate the square root of 4.02. Well, then I can write what my function is. It's just going to be the square root of x, because I'm taking the square root of some number that I'm interested in approximating. Well, the number that I know how to take the square root of is going to be 4, because that's really close to 4.02. And I also know that my change in x, well, my change in x should be a plus delta x is equal to exactly my x value. That's just looking at this picture here, right? I start at a, I want to go over by delta x, and I should end up at x. So if my a value is 4, and my x value is 4.02, I know that delta x should then be equal to 0.02. Well, then I can also find my derivative of x. That would be 1 divided by 2 times the square root of x, just by taking the derivative of root x. So then my derivative at my known point would be 1 divided by 2 times the square root of 4, which is 1 over 4. Yes? Yes. Okay. I also know exactly what my f of a value is, the function value at my known point. That's the square root of 4, which is also 2. So now I'm ready to make my approximation. I'd say that my value is approximately equal to my f of a plus my slope multiplied by my change in x. So this is equal to 2 plus my slope is 1 over 4 multiplied by 0.02. And this comes out to be, oh shoot, dang, I didn't bring my calculator. This would be 2 plus 1 over 25 times 1 over 50. And this is, give me one moment, I'll just do this on my phone. 2 plus 1 over 25 times 1 over 50 gives us 2.008. I believe. All right. Any questions on this? No questions on this example? All right. Then we'll do one practice problem. How are differentials different from limits? They seem the same. Differentials differ from limits in that with limits, we are shrinking this value of delta x. So that's actually a really good question. So with limits, we're saying what happens and delta x goes to 0. With differentials, we're saying, well, I know that I'm really close to a point that I do know, so I'm going to use the value that I do know and then use my derivative to make this tangent line approximation for my unknown value. So have you done tangent line approximations before? All right, so a brief overview of tangent line approximations. It's kind of like an intuitive concept. Let's say you have a function here. Well, the idea is if I take a tangent line at this point, well, for a lot of my function, it's a really bad approximation. But if I look only really close to this point, it's going to be reasonably close to my function value. And it's usually easier to evaluate a linear function than it is to evaluate something more complicated. So a tangent line approximation is saying my point here is close enough to my point here that I'm going to say this is a good approximation for it. And that's kind of the idea behind differentials. You're using them to approximate a point. With limits, you're finding the slope of that tangent line. So it's just kind of a couple of different use cases, I guess. Actually, we seem to be basically out of time for today, so we unfortunately won't get to some of the practice problems for differentials. But thank you for coming. I'm going to stop recording now.